Morning, student. This is Mr. Teo again. This is the one and the final last lecture of EG3959. I hope throughout all this lecture, you have learned something from it, and you have seriously go through all the lecture notes. And today, we just recap a bit. Last week, we actually talked about the open loop gain and the asymptotes, and basically we also look at how to create the both plot, basically the magnitude plot and the phase plot, using the 5 form that for each of them for both the magnitude and the phase. And after you successfully create the magnitude plot and the phase plot by aligning the magnitude plot on top and the phase plot below, we are able to check out what is the phase margin and gain margin. And through checking the phase margin and gain margin, if phase margin and gain margin are both positive, then we can conclude that the system stability is okay. That means it's stable. But however, if there is any one of them, for example, the phase margin is 0, then it's marginally. But if the phase margin or the gain margin went outside the shaded region, which is phase margin and gain margin is negative, then we conclude that the system is unstable. Now today, or rather this week, which is the last lecture, we are going to continue showing you more examples on the both plot, and at the same time we also will bring an introduction to you on a kind of PID tuning, which we call the Ziegler-Nicholas method of tuning. And then of course after that we will conclude the lecture. Of course you probably would like the background of a wave and sea and coconut tree. It looks like a holiday to you, right? So okay, this is deliberately chosen because it will be after this, after you finish your test, you'll be end your semester and probably you'll be enjoying somewhere with sea. And then of course you can hear the thundering around, right? So hopefully after this you will enjoy yourself and forget about the whatever that is taught, just for a moment. Okay, without further ado, let me basically start the lecture.
In previous lecture, we talk about Bode plot and stability analysis. This lecture we are going to continue chapter 5 by doing some examples on Bode plot and PID controller design. Also, we will introduce a method of controller tuning called the Ziegler-Nicholas method.
So basically, as I have just introduced already, we already did PID in week 13, and week 14 we talk about both plot and stability, which is last week. And today we are going to add on what we call the Ziegler-Nicholas tuning, and that basically ends the semester topic.
Let's continue the Bode plot by looking at example 1. A quick glance at the GH open loop transfer function shows that there is no 0 and 3 poles in the system. To get the phase margin and gain margin, the overall magnitude and phase plot have to be plotted. To get the overall magnitude and phase plots, each of the asymptotes has to be plotted. Let's look at firstly the poles at origin. S also means S plus 0. 0 means the roots is at 0, or we say is at origin. Recall form 3 of magnitude plot. We will draw a slope of minus 20 decibels per decade that crosses the 0 dB 1 radian per second point. For phase plot of the asymptote, we will look at form 3 of phase plot. It shows a minus 90 degree throughout the frequency span.
So basically, like what I have mentioned, we will go through some more examples on both plot, and this is one of them. So this example of both plot has no 0. So basically, there's no 0. They only have a gain value, and then you have 3 poles below, right? So for this, we also will be determining the phase margin, gain margin, and finally stability. So it's pretty standard kind of stability question or both plot question, right? So without further ado, we actually went into drawing out the asymptote for the phase and magnitude together, right? So basically for S is at origin, poles at origin. So basically your pole will slope down and cut the 1 radian 0 dp at slope of minus 20 degrees per decade. Of course, it cut at 1. Now, of course, this is origin because S is S plus 0, 0 is actually an origin, right? And then also, we know that for the phase, it will be a sloping down phase, but because it's 0, 0 is very far away. As you can see, if I divide 1 by 10, it will be 0.1, right? Divide by 10 is 0.01, but divide by 0.10 again, it will be 0.001. How many times do you need to divide in order to get to 0? It's like almost infinity, negative infinity. That's why 0, we cannot put it in the scale, so it's very far away. So therefore, for this case, the slope down, that means the slope down at 0, divide at 0, 0, and 0 times 0, right? So it's all 0, it collapses into a slope, fast slope, and go down all the way to here, which is minus 90 degrees, right? So that's, therefore, you only see the visible part, which is minus 90 degrees. So that is the gain and phase plot for the first one. And then, of course, next page will show you the second one and the third pose subsequent.
Now if we shift and look at the next asymptotes, that is 1 over s plus 1. Using form 5 for magnitude plot, we will have flat response from negative infinity to 1 radian per second. Thereafter the response will slope down at minus 20 decibels per decade till infinity. For the phase plot, again using form 5 of phase plot, the response will be flat at 0 degree for minus infinity till 0.1 radian per second. Thereafter, it will slope down at minus 45 degree per decade, and when it reaches 10 radian per second and flatten at minus 90 degree till infinity.
So basically, for the second one, we know the root is at 1. So of course, for the gain plot, it will turn at 1 radian per second, right? And it sloped down at minus 20 dB per decade. So this is very straightforward because it's a pole. Therefore, you will slope down at minus 20 dB per decade. It's not a 0. 0 it will slope up, poles will slope down. So that is gain plot, very straightforward. But for the phase plot, we have to not only look at 1 radian, but times 10 time, which is 10 radian, and divided by the 10 time, which is 0.1 radian. That is 1 decade down, 1 decade up, right? So the phase will start at 0, start turning at 0.1 radian, hit minus 45 degree at 1 radian, and then it will go all the way up to 10 radian, where it hit the minus 90 degrees and it will flatten. So basically, this is for s plus 1, right? 1 over s plus 1 term. Okay. Now the next slide will be showing you the at 5s plus 2.
Now if we shift and look at the next asymptotes, that is 1 over 5s plus 2. Using form 5 for magnitude plot, we will have flat response from negative infinity to 0.4 radian per second. Thereafter the response will slope down at minus 20 decibels per decade till infinity. For the phase plot, again using form 5 of phase plot, the response will be flat at 0 degree for minus infinity till 0.04 radian per second. Thereafter, it will slope down at minus 45 degree per decade, and when it reaches 4 radian per second and flatten at minus 90 degree till infinity.
So basically, the third term, slightly different from the second term, is that you got to calculate what is your root frequency. So you equate this to 0, it will be 2 over 5, which is 0.4. So the root is rolling at 0.4. So basically, it's a straight line for the magnitude plot until the root, it will slope down because it's a pole at minus 20 dB per decade. So that's as simple as that, right? For the phase, we have to look at bigger range, which is from 0.04 radian, which is 1 decade before the roots of 0.4, and to all the way to 4 radian, which is 10 times or 1 decade up from 0.4. So with that, we will have basically a 0 degree shift before 0.04 radian, and it will start sloping down at basically minus 40 degree per decade. And when it hit the roots, which is 0.4, it will be minus 45 degree, right? And then you will proceed going down at minus 45 degree per decade until it hit minus 90 degree at 4 radian, and there it will flatten at minus 90 degrees. So that's basically the third asymptote for magnitude and a phase, right?
The overall magnitude and phase plot, in black, is with the summation of all the asymptotes drawn on the semi-log paper plus the DC gain shifting. To check the phase margin and the gain margin, we need to use the overall magnitude and phase plot. To check the phase margin, we first look at the overall gain plot and check the frequency omega GC at which it crosses the 0 dB reference point. If we proceed downward along omega GC and check the value of the phase and take the difference between this phase and minus 180 degree reference point, we call this difference the phase margin, and it is 29 degree for this example. Note that the phase margin lies outside the shaded region. Hence, this is a negative phase margin.
So basically, just now what we have plotted individually for the 3 asymptote, right? And we just leave it here. And then, of course, after summing all, we get the black curve, which is the overall gain plot and the overall phase plot, right? With the overall gain plot and phase plot put over here to have a clearer view, and then we will start looking at the phase margin and gain margin. Now, for phase margin, we first look at the gain cutting the 0 dB, and then we look down to check when it cuts your phase, right? When it cuts your phase, it looks that is minus close to 200, and you check back to the reference of minus 180 degrees is actually having a phase margin of minus 29 degrees. Now, why minus? Because this time the phase margin is outside the shaded region, and the shaded region is basically bounded by the 0 dB point and the minus 180 degrees point bounded by these two. So this is the shaded region. So now it is outside the shaded region. So therefore, it is a minus phase margin, right? So that's one thing. Now, next page, we will try to look at the gain margin.
For the gain margin, we look at the frequency at which the overall phase crossed the minus 180 degree reference point, and we note this frequency as omega PC. If we look upward along omega PC and check the value of the gain at omega PC, take the difference of this gain with 0 dB. This will give us the gain margin. For this case is 9 decibels. Now again, the gain margin do not lie within the shaded region. Hence it is a negative gain margin.
So basically, for this case, again, now we are trying to look for gain margin. So gain margin, we have to look at when the phase cross the minus 180 degrees. And from this phase crossover point, you look up and you check what is the phase, what is the gain at this point, and measure it, how far is it away from the 0 dB, which is the reference point for the gain. And we realize that the gain margin is actually minus 9 dB. And this is again outside the shaded region, and that's the reason why it is minus 9 dB, right? So therefore, okay, next slide, we will conclude the stability status, right?
With both negative gain margin and phase margin, we can conclude that the system is unstable.
So basically, how do we conclude that they are negative? Because both the phase margin and gain margin lie outside the shaded region, which is bounded by 0 dB and minus 180 degrees. So because of that, both of them are negative. We can conclude that the system is unstable. So that is for example 1.
In this particular controller design, the specification for the system was laid down to be 0 steady state error, maximum peak overshoot less than 40%, and settling time using 2% criteria to be less than 2 seconds. There is no constraint on what kind of controller to be used, meaning we can use P, I, D, PI, PD, ID or PID so long as it meets the specification. The 3 specifications gave us some clues to proceed. Firstly, 0 steady state error can only be achieved by an controller with I element. Hence, our choice are now limited to I, PI, ID or PID. We will start off with the simpler controller and proceed slowly to the more complex ones. For the other 2 specifications, we can lift the formula from the formula sheet and form the equation as shown in red.
So basically, the example 2 is on controller tuning. So basically, this controller tuning is basically quite similar, or rather almost the same for Lab 7. Imagine the Lab 7 submission. You are supposed to do some calculation for the designing of the controller, and that basically this example guides you very closely to how to design. So first of all, the specs that required from the control design, they want a zero steady state error. As we already know, only controller or that give you a zero steady state error are the integrator, that means the I controller. So therefore, for this case, it clearly indicates that it needs an I controller. So therefore, the choice of GC has to include I. Whether it's an I controller alone, there's an I, or PI, or DI or ID, right? So these basically are the few choice that is with I. So therefore, I is included. And then they also mentioned that the maximum overshoot needs to be less than 40. So 40 is 40 divided by 100, which is 0.4. So this is your maximum overshoot or peak overshoot, has to be less than 40.4, right? And then, of course, also they say that the settling time for 2% criteria, this is the settling time for 2% criteria, must be less than. So less than should be, I think, the other way around, not this way. So it must be less than 2, okay? So maybe I should change this, just in case I confuse you guys. Less than should be the other way, right?
In this particular controller design, it was also...
Sorry, I try to adjust it back so that the sound goes away. So I go to the advanced to the next page and come back again. So that's why. So this will be a less than. So basically, these are the condition that is given. With this, we will proceed further. In the next page, we will show you how to solve it.
It was also given in the question the relationship between zeta and phase margin is zeta equals phase margin over 100 if phase margin is between 0 and 60. Also given in the formula for bandwidth, undamped frequency, settling time and maximum overshoot. All these formulas are also found in the formula sheet. If we use the maximum overshoot formula and equate it to 0.4, solving yield eta equals 0.28. But this solution is exactly at the borderline when maximum peak is 40%. If we move zeta to say 0.4, maximum peak would reduce to 31.6%. Well within the margin. Hence we go with zeta equals 0.4. Next, we use the third specification of settling time less than 2 seconds. If we give some margin and use 1.8 seconds instead and substituting zeta equals 0.4, we can solve omega n to be 5.56.
So again, of course, the other specs, or rather the other formula that is listed here, usually you can find in your formula sheet. So I'm not going to elaborate further. But with just now the previous two specification, the peak overshoot is given by this formula is less than 0.4, right? So of course, if we use exactly equals to 0.4, then we are just designing exactly at the borderline. What if the calculation is not accurate? It might fall outside or fall inside. So depending on choice. So a trial calculation of what is zeta, if we put 0.4, we get zeta about 0.28. But of course, we are not comfortable with this because this one lie exactly at 0.4. We want lesser than 0.4, right? So basically, if we try to shift this to maybe 0.316, something like that, so it's much smaller than 0.4, this still meet the spec, and then we calculate the zeta is 0.4. So basically, we want to use zeta 0.4 instead of 0.28 because 0.28 is just at the borderline. So using zeta 0.4, we use the other formula, which is 4 over zeta omega n. This is your settling time formula. And of course, if we use less than 2 seconds, let's say we give it around 1.8, then plugging the 0.4 in, basically we'll arrive at omega n equals to 5.56. So right now, what we have achieved is we found out what is zeta, which is 0.4, and what is omega n. Omega n is 5.56. Now with these two found, basically you will be able to find all the timing parameters, right? Timing parameters. So basically, next step, we will see what we can find.
With omega n and zeta found, we are almost able to define everything in this second-order equation. Assuming k equals 1, zeta equals 0.4 and omega n equals 5.56. We can reconstruct the second-order generic equation. For the controller choice, if we use iController and using Rule 7 in block diagram manipulation to simplify the closed-loop transfer function, we yield 8ki over s squared plus 0.8s plus 8ki. If we compare the closed-loop transfer function with the generic equation, the coefficients of the s term in the denominator cannot reconcile. Hence, iController alone cannot work. If we proceed using API controller, again using Rule 7 in block diagram manipulation, yield 8kps plus 8ki over s squared plus bracket 0.8 plus 8kp multiplied by s plus 8ki. Again comparing the closed-loop transfer function with the generic equation, we can now equate all the s square, s and non-s term.
So basically, just now we found zeta and omega n, not to find the timing parameters, but to reconstruct the generic equation. So with zeta and omega n, we know that the generic equation is given by k omega n squared plus by s squared plus 2 zeta omega n s plus omega n. So with this zeta and omega n, you just need to plug it in. Of course, we don't know what the value of k, but we can assume that k is equal to 1.
By equating each with omega n, if of each by equating
accidentally touch the cursor. So basically, if we use k equals to 1, then we plug in, then we will be able to find out the generic equation with k equals to 1 as this way. Now, why k equals to 1 also work? Because remember, I told you before that the most important equation parameters is actually the denominator, not the numerator. The numerator actually don't control the response that much. Basically, it's the denominator that controls it. So basically, the generic equation denominator is s squared. After using your this zeta and omega n substitution is plus by 4.44s plus by 30.86. Now with this set the basic ground for your PI designing, right? So if you want the PI controller with I, of course the simplest is just an I controller. So if just I controller, then your GC will be Ki over S, right? Nothing else. So if your GC is Ki over S, and we know that your transfer function for the plant is 8 over S plus 0.8, right? So you just your G will be KIS times by 8 over S plus 0.8. So it's G over 1 plus G. H is unity feedback, so it's done by 1. So if you try to solve this, you will get this equation, right? This equation, 8Ki over S squared plus 0.8S plus 8Ki. Now, if you compare this denominator of your closed-loop transfer function with the denominator of your generic equation, now S squared we can compare, no problem, very good. Now S term is a problem because this is 4.44S, but this one is 0.8S, so it doesn't reconcile. So which means that it's trying to tell us that no, you cannot just use an I controller to solve this problem because it's not compatible, right? So basically this idea of just using an I controller is out, so it's busted, right? This idea. So now the next simpler one without with I controller will be PI. Of course, you can say DI also can, but then let's try PI first, right? So if you have a PI, then we have a KP plus KI over S for GC, right? That's a PI controller. And then again, you replacing this back to by the PI controller with the rest remain, you have this formula, which is given by your rule 7. And then after simplifying this particular expression, you get this term. Now again, we start to compare the denominator again. S squared, no problem. S, can we equate? Yes. Now you have a KP term, so you can equate. And then how about the non-S term? Okay, no problem, 8Ki. So basically, for PI controller, it gives a green light, right? So basically, you can compare. And of course, if you can compare, you can design, right? So basically, with this, we will proceed to do the derivation for what is the value for Ki and what's the value for Kp.
By equating each of the coefficients of S square, S and non-S term, we would be able to solve for Ki equals 3.85 and Kp equals 0.38. A check on the simulation shows all maximum peak is achieved but not settling time.
Okay, so I took out the denominator for the generic equation and denominator for the closed loop transfer function. And then basically we need to compare this term to to derive Kp, and we need to compare this term with this term to derive Ki. So basically, the comparison is made here. You realize that Ki is 3.85, and if you compare the S term, you realize that Kp is 0.38. So with this Ki and Kp known, we basically put this back into your PI controller and run the simulation using the lab view, and we realize that, hey, for the maximum peak, we can achieve it because it's about 30-something%, right? So it's close, it's quite good. But the settling time, we require less than 2 seconds. But you look at it, for it to go within about plus minus 2%, it is almost like 2.5 seconds. So, or rather, is this 2.5 seconds? This is greater, 1, 2, 3. So it's 2.5 seconds instead of 2 seconds. So we want the settling time, which is less than 2 seconds, right? So basically, we need to fine tune this again because only one spec is met, the other one is not. So this is very normal for any design because the moment you don't meet, you got to reiterate again, slightly adjust certain parameter, run through the whole process again, and resubstitute and recalculate. So basically,
if we reiterate and use Ki equals 1 and Kp equals 20, a check on the simulation shows both maximum peak and the settling time specifications are achieved. In real-life design, first-round computed value may not meet all the specifications. Fine-tuning by recalculating iteration after iteration will eventually get us closer to the specifications.
So basically, you can see that if I change my Kp to 1 and Ki equals to 20, and you plug into the simulation and you realize that, hey, my maximum peak still meet, is still within less than 40%. And right now, my settling time is a lot better. It's about 1.5 seconds. So it's less than 2 seconds. So basically, it meets both of the conditions. So, but this one, it could be after many trials. You adjust this slightly higher, this slightly lower, and then recalculate and run the simulation. So it involves a lot of iteration. So which can be quite time consuming, right? So that is a part on the controller design by physical means. That means that you basically based on the spec, based on the formula, you just go and calculate and reiterate it. But of course, there is more efficient method than this, which we are going to introduce to you. One of them, which is called the Ziegler-Nicholas method. Ziegler-Nicholas method, basically they give you a table. Now, if you want to design a PID, follow this table and calculate. If you want a PI, you follow this table. If you want a P, follow this table, right? So the specs is all given, but of course, initially you have to calculate certain thing like the critical gain and critical phase, critical time. So once you calculate that, you plug into using the table, you should be able to derive all the values, right?
Next, we are going to introduce the Ziegler-Nicholas method for controller tuning. For Ziegler-Nicholas method, if we set Ti to infinity and Td to 0, we are essentially left with Kp, or rather the P, controller. By increasing the gain for Kp till certain point, the whole system will start to oscillate. This gain where Kp starts oscillate is called critical gain, and the frequency at which it oscillate is called critical frequency. Knowing the critical gain Ku and its period of oscillation Pu, the Kc, Ti and Td can be calculated using the Ziegler-Nicholas table for tuning parameters.
Okay, maybe I should go to the whiteboard and roughly explain this, because this method, this Ziegler-Nicholas method is important. Every of the tests or exam, always we come out Ziegler-Nicholas method. But unfortunately, we didn't put the tutorial question into the tutorial sheet. But we have one example here for Ziegler-Nicholas method, and a lot of time is always the same. It's just that the number is different. So if you would like, you may want to practice more on this Ziegler-Nicholas method based on the example, right? Okay, without further ado, let me just go to share with you the how to interpret what they mean by Ziegler-Nicholas. So Ziegler-Nicholas, the formula. Now where is my stylus? Now Ziegler-Nicholas, without further ado, they says that GC, that means the gain controller of Ziegler-Nicholas, is given by Kp bracket 1 plus 1 over Ti S this is S, right? Over S, TIS, so it's over S, right? Plus by TDS, right? TDS. Now again, you notice that this is I, so it's I controller, right? And this is D, so it's a D controller. So this is basically a PID controller. This is P, right? So it's a P controller. So basically the subscript is also specifically chosen. So if you try to multiply this thing out, basically is KP plus by KP over TIS plus by KP TDS. Now this is Ziegler-Nicholas, right? Ziegler-Nicholas formula. Now what about our conventional PID? Conventional PID, we have KP, which is the same, right? And our KI is KI over S, right? Now look at this. It's slightly different. So your KI is actually KP over TI, right? This is KI over S, right? And then of course this KDS, right? So your KD is actually KP TD. Oh, if you look at it this way, the conventional PID, we use it this way, and of course Ziegler-Nicholas use it and the other way. But of course there's nothing wrong, because it's really up to how you want to do it. But then he tried to group it in this way because you have to refer to his table to do the controller tuning. So basically it's just like that. Now what Ziegler-Nicholas advocate is that we can keep increasing this KP. KP, you can increase the gain from 0 to, let's say, infinity. And before it reach infinity, at some point, your whole system will start to oscillate, right? At some point, your whole system will start to oscillate. And he is actually interested in this gain that it start to oscillate when it start. That means, okay, when does a controller start to oscillate? At first, you reduce your, increase your gain. Increase your gain, if you remember, your damping ratio will change. Got one of the example, as we increase our KP, your zeta will change from 0 to maybe between 0 and 1, right? Between 0 and 1, then it will change to 1, and then finally it will be greater than 1, right? So basically your zeta will run, right? At some point, okay, so this part is still oscillatory. This part 0 is of course oscillatory, right? And then of course between 0 and 1, it is slightly oscillatory because it's under them. Now this is of course stable, and this is stable because this is greater than 1. Let's say 10. Of course this is stable, right? So if you change your gain by moving it higher and higher, KP increase, right? By moving it higher and higher, right? At some point, at this point, this will be the start of oscillation. Start of the oscillation. So as your gain increase, when it hit the under dam, that will be a start of oscillation. So basically, when it fully oscillate, of course, when it is undamped. So basically, increasing your KP will result your damping ratio to move from over dam, critically damped, under dam, and undamped. Of course, when it's critical under dam, it will start oscillation. So basically, what it's trying to say here, if I have so the key parameters that Ziegler-Nicholas advocate is basically your critically gain. That means the gain whereby it start oscillation, and the frequency whereby it start oscillation. So which means that if you increase until, let's say, a certain point around here, around this region, okay, this frequency that it start to oscillate, let's say we call it the critical frequency, right? And then the gain that you increase up to this point, we call it the critical gain. So he's interested in finding out what is this critical frequency, because it used it in the table, and what is this critical frequency, right? Where he used it also as period in he used the critical period, not the critical frequency. And basically with these two, he will basically be able to use the table and calculate your PID coefficient. Now, do take note that in his condition, he set when he vary the gain is he set Ti equals to infinity, Ti approach infinity and Td approach 0. Right? When Ti approach infinity, Td approach 0, basically you are getting rid of the I term and a D term. You just use a Kp term for your experiment, right? So basically, when it start oscillate, of course, that will be your undamped case when you start oscillate. So this frequency here will be your, this will be your omega Cr, which is 2 times FCR, right? This will be your frequency of oscillation, omega Cr. Then whatever gain that you achieve, the starting of the oscillation, that will be your KCR, right? So that's what Ziegler-Nicholas is talking all about, right? Now, let's go through the example before we conclude what Ziegler-Nicholas has to say by following the lecture notes. So basically, what happened?
With both negative gain
Sorry.
in this particular
Stop sharing first. I think somehow something go haywire. Let me share the Ziegler-Nicholas. Something go haywire just now. Okay, where is the Ziegler-Nicholas? Okay, we just finished at this page, right? So basically the next page will be this one.
In this particular, it was with omega by equating if. Next, we are going to introduce the Ziegler-Nicholas method for controller tuning. For Ziegler-Nicholas method, if we set Ti to infinity and Td to 0, we are essentially left with Kp, or rather the P, controller. By increasing the gain for Kp till certain point, the whole system will start to oscillate. This gain where Kp starts oscillate is called critical gain, and the frequency at which it oscillate is called critical frequency. Knowing the critical gain Ku and its period of oscillation Pu, the Kc, Ti and Td can be calculated using the Ziegler-Nicholas table for tuning parameters.
So of course he denote just now I use KCR and PCR, right? He to denote it as Ku and Pu, so it's the same thing. So once you know your Ku and Pu, you can plug it inside. Let's say you want a PID, you just Ku, Pu all here. So you can calculate your coefficient for your Kc, for your Ti and Td. So once you can calculate the value for each of these, you plug it back to your equation, and that's it. That's the design of your PID. Now if you want Pi instead, you just use this and this, right? Without the D. So Pi. So if you want a P, just a 0.5 Ku. So that's extreme simple as that. Versus your previous example, you have to calculate, recalculate, and reiterate, calculating it over and over again. So this is a lot more simpler, right?
For example 3, if we set Ti equals infinity and Td equals 0, Gc will become a P controller. The closed loop transfer function using Rule 7 for block diagram manipulation will be Kp over S. Bracket S plus 1 bracket S plus 5 plus Kp. If we do a Bode plot for the 4 asymptotes and find the magnitude and phase plot, we would be able to determine the gain margin for this plot.
So basically, the example start by saying that, hey, we don't know what controller we want, of course. Then we will design the controller, but we have the plant expression, right? So this is your plant expression. Now, let's say we assume we are using P controller, Kp, right? Because remember when you do your Ziegler-Nicholas, your I and your D is set to infinity and 0, basically to nullify the I and D effect. And basically you just use a P to plug in, and we change our P from 0 to certain value where it starts to oscillate, which is Ku. So basically, so if you plug in the equation as Kp and then you rewrite and calculate your expression, you will end up using rule 7. You end up as Kp over S plus 1, S plus 5 plus by Kp. So with that, you can do a Bode plot, right? Because this is a closed loop transfer function. Of course, you don't do a Bode plot. But then if you do an open loop transfer function, it will be Kp multiplied by this whole transfer function, right? So it's basically Kp is depending on what is the value, but you know that there is 1 pole, 2 pole, 3 pole. So 1 pole is here, 2 pole is here, 3 pole is here, right? So because this guy here is nullified to 5 over 5 and S over 5, so therefore is S over 5 plus 1. So, or S over 5 is actually 0.2 S plus 1. So the 1 over 5 is as a result of bringing out the 5 over here, right? So this is 1 over 5. So basically your DC gain is 1 over 5. The rest of the asymptote is just as follow. So if you were to plot their...
We would therefore be able to equate 20 log KCR to the gain margin and solve for the critical gain KCR. For omega CR, we just look at the frequency at which the phase cross minus 180 degree. This case here is crosses at 2.3 radian per second. Hence omega CR is 2.3 radian per second. To find PCR we just use PCR equals 2 pi over omega CR. This case is calculated to be 2.732 seconds.
Now, of course, you can go through the entire steps of the book plot to get a final resultant gain plot and a final resultant phase plot. But of course, this one we use simulator to simulate it. So from here, your phase, when it crossed the minus 180 degree, you can check for the gain margin. In fact, for Ziegler Nicholas, we are only interested in the gain margin. We are not interested in the phase margin, right? So basically, if you look at the point where it crossed, you look up, you check the gain margin. The gain margin is 29.6, right? So if gain margin is 29.6, that means 20 log KCR, the critical gain, is equals to your gain margin. Because why? Because if we start to shift this guy up to this point, it will means that your gain margin will be 0 at this point. Because if your gain is shifted up by this much, right? If your gain is shifted, remember when we shift gain using the DC shift, we shift the whole transfer function up. So if you shift the gain up by 29.6 dB, your gain margin is essentially 0. Now above and beyond it, it will be oscillating already, right? Because negative phase margin is not stable. So therefore, using this gain margin information, if you equate it, so my KCR is approximately about 30. So if I shift my KCR 30 times, that means increase my gain by 30 times, it will probably oscillate. And it will oscillate at what frequency? It oscillates at this the phase crossover frequency, omega PC. And then if you read it, it's about 2.3 radian per second. So 2.3 radian per second is the omega critical omega frequency. And omega is actually 2 pi over f, right? Omega is actually 2 pi over f. So basically, if you have f is omega divided by 2 pi. So basically, you just need to rearrange the calculation, and you will be, because if you know what is f, this is 2 pi f. If you know what is f, then basically your PCR is just 1 over f, right? It's 1 over f. So you can calculate it, and basically you get your PCR and KCR, or this is also equals to your KU and PU in the table that we mentioned just now, right?
After determining KCR and omega CR, we let KCR and omega CR equals to KU and PU. Using KU and PU, we can determine KC, TI and TD for either PID, PI or P controller. In this example we are finding the coefficient for PID controller. Hence we can use the formula and calculate for KC, TI and TD and their values 18, 1.366 seconds and 0.342 seconds respectively.
So basically, just now we calculated the KCR and PCR, basically is your KU and PU. So once you know your KU, PU, you just plug in. Let's say I want a PID controller. I just plug in KU here, I just plug in PU here, and I just plug in PU there, right? So basically for each of your coefficient, you can calculate that by bringing out the formula. KC is equals to 0.6 KCR. So 0.6 times by the KCR that you calculated in the previous speech give you 18. Now TI is 0.5 times by PCR. The PCR value that is you calculated in the previous speech, you give 1.366, and so on and so forth for TD. So once you calculate all these, you can reconstruct your
Referring back
PID,
to the formula sheet, GC can be constructed from the calculated KC, TI and TD.
So basically, once you get all your KC, TI and TD, you just plug it into this equation, and this is your PID equation, the controller equation So that's as simple as that. So the system plant will be designed with PID controller of this value. Instead of keep recalculating, you just substitute in using that table. And of course, in the exam or test, if I need you to do the calculation using the Ziegler-Nicholas, the table will be given. Okay.
As we can see, the unity feedback without controller, the rise time is not as fast as that with a PID controller.
So this page is trying to see the one without a controller. So basically, a system without a controller basically will rise slower, right? So it's not modified and it's quite sluggish. So in terms of rise time, is taking very long time. Let's say talk about 0 to 100%, it takes about 18. This is 2, 4, 6, 8, 10, right? So 2, 4, 6, 8. That's about 18 seconds to get into the close to the final value. But if you look at the one with PID control, straight away it goes all the way up in 1 second, right? A hit 1 second at value of 1, amplitude of 1 at about 1 second time. So basically with feedback, it really speed up the whole rise time. But of course, you got if you design an under them case, you got pick and throw. But important thing is finally it settled down, right? So it is still okay. Rise time is okay. It settled down. It's pretty good, right?
Please watch tutorial 15.
So of course, like I always advocate, there is a tutorial 15 at your tutorial column, which is recorded by Michelle Go, and that you can watch her explanation on how to solve question 5 and 9. But again, I'm going to handhold you for question 5 and question 9, and then after that we will finish this session. So basically, right now, let me go to the question itself for tutorial 5. So first of all, we want to talk about question 5, right? Now question 5 is pretty easy because the transfer function is 10 over s plus 1, right? So they ask you to draw on a semi-log paper the asymptote and magnitude plot of the system. So this is doing your book plot and determine the gain and phase margin, right? Then secondly, introduce another pole to the system and redetermine your gain and phase margin. Then finally, it says that it requires the system to have a minimum of 10 dB gain margin and phase margin of 30 degrees. Determine the K required to meet this. That means if I want to shift my gain, how to do this. So basically, it looks simple, but at the end, it is, for example, part C and part D, it gets more complicated. Right? But nonetheless, let's go and take a look at the solution. Let me stop share first. Let me stop share first. I need to search for the solution. Okay, let's present the solution for question 5, right? Now, question 5 is again this expression. So if we look at it, there is how many pole? 1 pole, 2 pole, right? The first pole is this guy here, which is the green line, whereby the pole cuts the 0 and 1. So this is your first pole. Now the second pole is the is the black line, right? Now the second pole is actually the green line, which has a turning at 1, right? Turning at 1, the roots at 1. So basically that's the 2 line, right? These 2 line. Now the red one is your gain, which is 10. So 20 log 10 is 20. So this is your DC shift. So if you try to plot the thing, it will look something like that and then bend down from minus 20 dB per decade, you'll bend down to minus 40 dB per decade. But after you shift, it will shift to this orange line, minus 20 dB per decade to minus 40 dB per decade. So this is your gain plot, right? Now phase plot, also quite straightforward. your S term is basically minus 90 degrees. So that's why you have your minus 90 degree line. And then the other term is rolling off at 0.1, right? So 0.1 is here, 1 is here, and 10 is here, right? So it start to roll off at 0.1 and then hit 90 at 10, right? So it's stopped here. So basically, if I were to combine this and this, basically at this point, it should roll off, right? It should roll off. Sorry, it should be this curve, not that one. Just now it should be start at 0 and then roll off at 10 and then flatten for S plus 1, right? S plus 1. So now if you add this one and this one, you 0 add with minus 90, you get minus 90 and so on and so forth, right? You follow this line and then it will stay put at minus 180 degrees because you got two pole. Remember, one pole introduced 90 degrees, so two pole will be introduced minus 180 degrees finally. So with your gain and phase plot in, so now we look at gain phase margin. When the gain plot cuts the 0 dB, when a gain plot cuts the 0 dB, you will see that there is 18 degrees phase margin. Now when the phase touch or cut the 180 degree, you see that the gain margin is 20 degrees. So basically, this is both positive gain margin and positive phase margin. I would say that it is stable, right? I would say that it's stable. Now let's go back to the question again. It asks whether the determine the gain margin and phase margin of a system we already determine and whether it's stable or not, right? Now, if they say in the part C, they introduce a pole at S plus 2. So meaning that they put one S plus 2 below here at the denominator. And they ask you to redraw the whole plot and how does it affect the gain and phase margin. So with this, we introduce another one. So at S equals to 2, so this is 2, we introduce the S plus 2 here, right? S plus 2, right? So we introduce another pole. So with this pole, it actually modified the plot from here, it turned down some more, right? It turned down some more. So you can see at 2, instead of going straight, it turned down to minus what? Minus 60 dB per decade, because now I got 3 lines, 1, 2, and the black line 3. So 3 line that is going down, each slope at 20 degrees. So this is minus 60 dB per decade. So this is your final gain plot with your S plus 2 introduced in. Now, what about the phase? The phase also has an impact because this blue S plus 2 also shift the phase at from 0.2 to 20, right? So effectively, if you draw it out, your phase will be affected and shifted more. Instead of stopping at minus 180 degree, now it stopped even lower, about much lower than that, right? So basically, it shifts into this way. So with these two now let's check the gain margin and phase margin. For the gain plot that crossed the 0 dB, we look down. Now the gain margin is outside the shaded region, which is minus 18 degree. Now let's look at the gain margin. Gain margin is when the phase cross the 180 degree, we look upward. Now gain margin right now is also minus 8 dB. So by introducing an additional S plus 2 at the bottom, basically cause both the gain margin and phase margin to go negative, right? So as a result, before it was 20, after that you become minus 8. Before the phase margin was 18, now it becomes minus 18. So basically, both your gain margin and phase margin greatly reduce, and it reduced to a negative region. So therefore, the new system is unstable after the pole is added, right, into the system. So basically, you add a S plus 2 pole in the denominator, it results in instability, right? So how does the pole affect the GM and phase margin? So basically, it reduces the GM and phase margin. And what is the net cost? Of course, net cost is it causes it to be unstable. Now, the last part here, it says that it requires that a system should have a minimum 10 dB and 30 degrees phase by shifting the gain. So now the last thing they want you to perform is, you already know what is your phase margin, gain margin. Now, how can you shift this gain plot up and down to achieve a gain margin of 10 dB and 10 dB or more, or phase margin of 30 degrees. So we can see from the following, if we were to shift the if we were to shift the gain margin in such a way that it cuts earlier, right? So before that, it was cutting much nearer to here, right? So if you shift your gain, if you lower your gain, lower to a certain point, right? You should be able to get better phase margin. You follow what I mean? So if you reduce your gain plot to say around here, so if you bring your gain plot down parallel, in a parallel fashion, you just bring a gain plot down. So now your gain will cut your 0 dB at an earlier fashion. Before it was cutting here, right? Now it's shift to cutting here. Now by shifting to cutting here, you get about 36 degree. So which meets the objective. You need a phase margin of at least 30 degree, right? So if you shift it down to here, you get 36 degree. And then if you check your gain margin, you look back up, oh, this is about 13 dB. Can you read 13 dB? So therefore, by shifting the gain from 20 dB to 0, basically you drop it by 20 dB. Then you'll be able to achieve the specs, right? Of more than 30 degrees phase margin and more than 10 dB gain margin. So that is your answer for part 3, which is determine the K value. So K will be, of course, you got to recalculate the linear portion. 20 dB is in the dB fashion, so you got to change it back to the non-dB version, which is what is the value? Must be about 0.1 time. So if K is 0.1, you take 20 log 0.1 is minus 20 dB. Right, 20 log 0.1, 0.1 is minus 20 dB. You can test it by the calculator. 20 log 0.1 will give you minus 20 dB. So your gain will drop by 20 dB if you just multiply by 0.1. Okay, so with that, we still have one more question, right? Am I correct? Of course, the other question is question 9, which talk about methods of controller tuning. So this one, I can straight away flip down to question 9 to show it to you. Of course, you may have seen that, wow, this one look very complicated. In fact, this one I don't mean to share with you guys, but because the question is there, students start to ask me and I start to solve. So once I solve already, I just present it as a solution. But in fact, such a question that is more complex in nature, I won't test you in your final exam or test or whatsoever. So if I'm not testing you on all these things, there's no point going through it. So you will make your brain even tougher. So right now I'm going straight to question 9. Question 9 talks about where's question 9, by the way? Question 9, it says that other modes of control tuning. Of course, we learn about Ziegler-Nicholas, but the other 3, since few semester ago, we took it out because we say that, hey, since we never test you on step change or lumbar tuning or trial and error tuning, then we will take out. So since I take it out, I don't think I will ask you such kind of question, whether is there any more other kind of control tuning. I just need you to know that there's Ziegler-Nicholas method, that's all. Right? So with that, of course, I'm sorry for the, as I flip the PowerPoint, the sound start going haywire. Sometimes that's the sad part about if you try to record your sound inside your PowerPoint slides. If you sequence is not right, it will garbage out. So, but anyway, we meet our objective by completing it, and I hope all of you enjoy it, and I wish you all the best in your final test and for graduation. Okay, thank you and bye-bye.